Problem 16. Derive planar density expressions for FCC 100 and 111 planes in terms of the atomic radius r. Compute and compare planar density values for these same two planes for nickel. Okay, let's do the part A first. So in part A there is this FCC unit cell. So this is the FCC unit cell. In this unit cell there is a plane 100. So 100 plane is this plane. Okay, 1, and then 00 means this plane is parallel to y and z axis. Okay, so 100 plane will be this plane, this front face. That means A, B, C, D will be the 100 plane. Okay, so for this plane the planar density PD we need to find. So the planar density is equal to the number of atoms associated with this plane and divided by the area of the plane. So what are the how many number of atoms are associated? So since this is an FCC structure, so there are 5 atoms so at the corners. So for example 4 atoms at the corner and 1 atom at the center. So since these diagonal atoms will be touching with each other, so the diagonal will be equal to 4r and the length will be, then we can find, so which is equal to a square plus a square is equal to 4r square. So you can find a is equal to 2 under root 2 r. So and how many atoms are there? So at each of the corner 1/4 of the atom is associated and the central atom is fully associated. So 4 atoms times 1/4 plus 1 atom is fully, so there will be 2 atoms which are associated. So the area will be equal to 8r square. Okay, so planar density for FCC in the for 100 plane, it will be equal to 2 atoms divided by area. So area is equal to a square, because this is a, so area is equal to 8r square. 8r square, it will be equal to 1 over 4r square. Okay, so this is for 100 plane. How about 111 plane? So again I can draw this FCC unit cell. Okay, so draw these coordinate axes. Okay, so what is 111 plane? 111 plane is one of the point is here, one of the point is here, and then one of the point is here, and then this will be this triangular plane. Okay, so this triangular plane, so it's in this triangular plane, this side is in this plane. Okay, so for example if I say that it is A, B, C, D, and then if I say it E and then F, so this side CE is in this plane, BE CF, that means on the right side that plane. So and similarly this side AC will be in this front plane. Okay, and then this the lower side is in the lower plane. So as you can see that this is a cubic structure, so all these three sides will be equal. And for example, if I want to find the length of this side, it will be a square plus a square. So this length of this, so this plane, okay, let me draw this plane, this over here. So this plane will be a triangular plane. So there is one atom, and over here one atom, over here one atom over here. Okay, and then one face atom from here, one face atom from here, and one face atom for here. So all these 6 atoms will be touching with each other, although it's not showing like this over here due to the poor drawing. So but these atoms will be showing will be touching with each other. So what is this length? So this length is since this is the face diagonal, so face diagonal is equal to the face, these two faces, and then this is the face diagonal. Okay, this length. So this face diagonal square will be equal to a square plus a square, so it will be 2a square. So this is the face diagonal, and then we know that a is equal to 2 under root 2r, or a square is equal to 8r square. So face diagonal square is equal to 2 times 8r square. So it will be 2 times 8r square. So it is equal to 16r square. So it is 16r square, so it means that it is equal to 4r. Yeah, actually it was quite simple, because there's these 3 circles are touching with each other, so definitely, obviously, this is equal to 4r. Anyway, so what is the area of this triangle? Since this is an equilateral triangle, so the area of this triangle is can be determined by this right angle. So the area will be equal to area of this triangle. Okay, the area of this triangle is equal to area of these two small triangles. So one area of this left side triangle is equal to 1/2 the base. So this base will be 2r. Okay, 2r times height. So this height is equal to 4r times sine 60 degree. 4r times sine 60 degree. So this is the area of this triangle left side. So right side triangle is the same as the left side triangle, so multiply it by 2. So if you simplify it, then it will be 4r square under root 3. The number of atoms in this one plane are can be determined by this. Since this is the triangular plane, so there are 3 atoms along this each of the sides. So the corner atoms are 1/6. There are 3 corner atoms. These middle atoms are 1/2. So there are 3. So total is 2. So planar density for FCC in the 1 1 1 direction is equal to 2 atoms divided by 4r square, that is the area. So 1 over 4r square under root 3. Okay. For part B, it has been asked that what is the planar density of nickel in along these two directions. So the atomic radius of nickel can be found from the book, or it can be searched from the internet. It is equal to 0.125 nanometer. So planar density of nickel in 100 direction will use this expression. So 1 divided by 4 into 0.125 times 10 to the power 9. So convert nanometer into meters. So it will be this. So you will have 1.6 times 10 to the power 19 per square meter, atoms per square meter. And for the planar density of nickel in the other plane, planar density of nickel in this 111 plane, it is equal to 1 divided by 4, it will be 1 divided by 4r square under root 3. So if you input these values over here, so this value will be equal to 1.848 into 10 to the power 19 per meter square. So you can see that the planar density of nickel in 111 plane is slightly higher than in 100 plane. There is this small there is this correction, that because it was 2, it was 4, so it should be 2 here, 2r square. Okay, so similarly it should be 2r square.